Hello, my name is Jonathan Guerrero, and for my presentation, I will be talking about polymeric biomaterials. And so first, what exactly is a biomaterial? So biomaterials are materials that interact with biological systems and are widely used in the medical and biotechnology fields in all sorts of medical devices and products, such as prosthetics and implants. Biomaterials can be made from synthetic or natural materials, and this will often depend on the intended use case for the device or the implant that the material will construct. Um, as for what makes a good biomaterial, the important characteristic of a biomaterial is that it is able to interact with the body and fulfill its intended purpose without causing any harm or any other unintended negative effects. Essentially, you want something that's non-toxic and that's able to withstand the environment of the human body, although the second point is dependent on the intended use case and the location within the body of the material. And so the challenge of developing and choosing biomaterials is that the human body is a delicate environment and every part of the body will present its own challenges as well as each individual body. And biomaterials can have a range of interaction with the surrounding tissue when inside the body. Inert means that the material has minimal interactions with tissue, whereas resorbable is more interactive and they'll often dissolve when introduced into the environment of the human body. And biomaterials can range anywhere between these two characteristics. So for biomaterials, they have the same classification as the one that we learned for general materials in our first lecture, in which they are divided based on their properties and their structure. The three types of biomaterials are metals, ceramics, and polymers. They all have distinct properties and uses. Metals are typically inert, meaning that they interact minimally with the surrounding tissue, and thus can have a high lifespan within the body. Metals are often used for their tensile strength and their durability, and they are used for typically load-bearing applications, such as in the replacement of joints like the knee or in the hip. Examples include 316 stainless steel and titanium. But despite these strengths, they can be susceptible to rust and corrosion. Ceramics are hard materials that have a large range of interaction with the body and thus can be either inert, resorbable, or anything between. They are hard and wear resistant, which makes them good for use in surfaces on medical devices and implants, and also as scaffolds for bone growth for the resorbable types of ceramics. And so examples of ceramics include alumina, which is an inert, and calcium phosphates, which are resorbable. And so as you see in the pictures, we have a knee replacement, which is made of metal. And then we have teeth dental implants, which are made of ceramics. And then the third type is polymers, as said before. And so for the polymers properties, they can be either inert or resorbable. It's largely dependent on the type of polymer. They're easy to manufacture, at least relatively to the other types of biomaterials, and they're very resilient inside the human body. They're very flexible, which makes them good for a large range of applications, and they're easy to process. And that a unique property of them is that you can blend them to change the properties, make them more elastic or less elastic, or whatever you need for your specific application. The structure of polymers, they are carbon-based chains that are made up of simpler molecular units called monomers, and these monomers repeat in sequence and form long chains, which are then known as the polymer. These monomers are connected with covalent bonds, and they can have synthetic or natural origins, although naturally originated polymers often degrade easier. And they can be formed into a variety of structures such as films, hydrogels, or 3D structures. And at the bottom you can see some examples of monomers. Those are the single unit that when repeated and put together will create large chains, which is then the whole polymer. As said earlier, polymers have a large range of applications. They can be used in hydrogels, which are a 3D network of polymer that can hold an increased amount of water. And these are formed by adding ions to the structure, which causes the chains to cross-link with covalent or non-covalent bonds. Um, Along with films, which are assembled layer by layer, they can be used for wound dressings and to cover up burns or large lacerations. Scaffolds for um, tissue or bone growth can also be made. These absorb into the surrounding tissue. And then low friction surfaces are often used with polymers. Examples would be valves like within the heart. And then here we have the 3D model. Um, Here's a 3D model of polyurethane, which is used in heart valves. And this model was constructed using MolView, a modeling software. And that is just the single monomer. When repeated and put together, would create a large chain. And then in this uh, model, nitrogen is blue, oxygen is red, carbon is gray, and hydrogen atoms are white. And thank you for watching my presentation.